Hi everybody, it's Mr. Mullicash again. This is our week 12 video for Math 172 online with Johnston Community College. There's my email address. If you're watching this video and you have any questions about what you see here, I will warn you that we're talking about vectors this week and next week. So this video is really going to be for both week 12 and 13. For this particular semester where I'm taping or videoing this. In future semesters it may just be 12 or 13, but there's a lot of stuff to talk about with vectors, so I'll introduce what vectors are in a moment, but I've copied this from our course's ALEX syllabus. This is the stuff that you're supposed to do in ALEX, and for this particular semester this is the day that it's due. It's really the 20th because the 21st is a holiday. That's the day we have off before Thanksgiving Day, right? And as you're looking at this, maybe you can pause this video to look at all these words, but there's likely a lot of stuff in here that you've never learned before. Much like the polar coordinates and polar functions that we did in the last week's video. The word vector may be new to you. The terminal and initial points, component form, scalar, dot product, all this stuff is just kind of, it's a little overwhelming. So the good news is you have a little extra time. It's, the week plus the short week for Thanksgiving before all this is due. And I'm going to give you a brief overview of some of these key components, and I will tell you that in Blackboard, if you're taking this class online and you have me for your instructor, in this week's weekly assignment folder, I've put a lot of different videos for different topics. So I will say that when you're going through this in ALEX and you go through a topic and you struggle with something, if you're struggling, like let's say you don't know really what ALEX was trying to show you with unit vectors, or you didn't perform well on unit vectors, then I would go back to Blackboard and I would go in this week 12 folder, and there's a video on unit vectors in the folder. There's videos on dot product. There's videos on scalar multiplication. There's videos on magnitude. There's lots of Patrick JMT videos I've put in there, as well as this one for me. So there's no way that all of this can be written down or covered in one video. It would be an hour, it would be hours long. So again, my advice to you is to go, after watching this video, and again I'll give you an overview, but go through ALEX, look at the different things that you have to do, and when you get stuck on something, I would go, get some extra help by going to one of the Patrick JMT videos that I put in the weekly assignment folder. Okay, so let's go talk about what a vector is. What is a vector? A vector is a quantity. It's something that can be measured, but this vector has two different measurements, right? A vector is a quantity that has magnitude and direction. And when we draw a vector on graph paper, or maybe some other diagram or something, it looks like a ray. It looks like you have one point, and coming out from the point is an arrow, right? Now the arrow ends at a certain other point, so it's a little deceiving, but the arrow doesn't mean that this goes on forever. It means that we're going from one point to another in a certain direction. Okay, and the distance between the 2 points is called the magnitude. So let me go repeat that again in case you're writing this down or taking notes. The direction is we're going from one point to another point, and this direction can be measured by an angle, by solving a right triangle or so or whatever. But there's a direction that the thing is moving in, right? From the vectors moving from one point to another. So we could have started up here and drew the arrow this way, but you would never have two different arrows. And the magnitude is the length from one point to another. So the magnitude is independent of direction. It doesn't matter which direction you're going in. It's the same distance. All right, so imagine that this is home and this is Johnston Community College. You know, in one direction, you'd be driving from home to Johnston Community College, and then maybe after you have a class on campus, you go from, or tutoring or whatever, you go from Johnston Community College back to home. Well, you've driven two different directions, but you've driven the same magnitude because it's the same distance both ways. So that's pretty much what a vector looks like on a graph. Okay, now, so in order to get these things written down, there's a couple of ways that you can name a vector. Vectors have names. You can call it vector V. It's in bold, right? So that's red vector V. Or you can have a V with a little arrow over the top of it. And there's even other ways beyond this that you can use notation for vectors, right? Okay, so vectors have components, and I'm going to draw those in a different color because they're not actually part of the vector itself, but they're different measurements, right? So this point is called the initial point. I'll put okay, and then this point up here is called the terminal point. I think my M has got an extra hump there, but anyway, terminal point. So the direction is indicated by going from the initial point to the terminal point. Initial means beginning, terminal means ending. And in the vector, we can measure this vector with two components. Okay, so one is called the horizontal component. And you guessed it, the other one's called the vertical component. Okay, so for example, let's say that this length was 3 units to the right and this length was 4 units up. So we can do two different vectors added together to make the final one. And you'll learn more about vector addition geometrically and algebraically in ALEX. But if you go to the right 3 and then up 4, it's the same thing as going 5 units this way. And you might say, okay, well, here's A. Say, where did the 5 come from? And there's B and there's C, right? So, you know, if this were 3 and this were 4, then the vector components would be 3, 4. You say, whoa, wait a minute. Did you say less than 3, comma 4 greater than? No. These are not less than and greater than signs. These are angled brackets. Angled brackets. So, you know, like if you say 3 less than 4, that's one thing. But if you say 3 comma 4, these are a little bit, well, quite a bit more stretched out. They're kind of like parentheses, but they're angled, right? They're called angled brackets. So these are used to write a vector in what we say component form. All right, so how long is C? Well, to figure that out, you just do the Pythagorean theorem, right? And if you do that, you get C is 5. So 5 is the magnitude of vector V. That's 5. So the formula for that is the square root of a squared plus b squared, where A and B are the components. Okay. Again, I understand this is a lot of information, so take your time going through ALEX, and if you get stuck on something, there's lots of other videos in the week 12, 13 folder. Okay. What we need to talk about before moving on, though, is what another way, I suppose, of writing components. So let's say that vector V has components 3 and 4. Okay, we can scale those components down to where each component is exactly 1 unit long, right? So if we drew our initial point and our terminal point, we had the vector going like this, and this length was 3, and this length up was 4, okay, we can divide these up into little units. So let's say that there's a vector that's 1 unit long, there's a vector that's 1 unit long, there's a vector that's 1 unit long. So this is 3 times what we call a unit vector. Okay, the unit vector in the x direction, or the horizontal one, is called I. Okay, so that's going to be called the horizontal unit vector. That's called I. So we can multiply that by 3 to get our component, right? So we can say that this vector is got components 3, 4, but we can take 3 and multiply it by vector I and add it to 4 times this other vector. So there's going to be 4 unit vectors this way, 1, 2, 3, 4, and that is a vertical unit vector, and that is called J. And if you go on and take Calculus 3, or if you watch all the Patrick JMT videos, there is a K vector which goes into a third dimension. So you can have I, J, and K, and it doesn't mean I'm just kidding, I, J, K. It just means that they're different unit vectors in different directions. But the J vector is what we would multiply here. Okay, so you can get vector V by taking 3 i's and adding 4 j's together. Okay, so again, that's a vector that is written in component form, but this is written in terms of its unit vectors in the horizontal and vertical directions. Now, while we're here, we can really need to talk about the fact that the original initial point could be anywhere on the graph. We could pick the initial point anywhere in the graph. So it could be your home, it could be my home, it could be Beijing, it could be anywhere, right? But we're going to say that this is x1, y1, and this is x2, y2. Okay, so what we know, if we want to find these components, and all we know is the initial and terminal point, what we need to do is find the rise and run, right? So if these numbers are a and b, then a is x2 minus x1, and b is y2 minus y1. And that should look familiar to you because that's the run and the rise. And you would do 4 divided by 3, of course, rise divided by run to find the slope of the line. Okay. You may need to solve not only for the hypotenuse, but you may need to solve for this angle right here. And this may sound familiar from last week, but this angle's tangent is b divided by a, which is the vertical component divided by the horizontal one. So you can find that angle by doing inverse tangent. I will warn you that if the angle is not in the first or fourth quadrant, that you'll have to add 180 degrees or pi radians. But with triangles and vectors, we're almost always going to use degrees. So you'd have to add 180 degrees to get into the second or third quadrant. Okay, so that's important stuff to remember. And again, I'm just giving you sort of a brief overview so you can kind of like get a taste of what all this is, right? So we wrote a position vector in terms of ai plus bj. We told you what happens with initial and terminal points. Talked about how to find the magnitude of a vector in either this form or component form, and really these are the same thing, just written differently. Linear combination of vectors, right? So that's something you'll go through in ALEKS. We talked about unit vectors. All right, what's multiplication of vector by a scalar? What's a scalar? Okay, so let's go back to our picture here. A scalar is another way of describing like a scale factor, or how to make the vector longer or shorter. So if I had 2v, what I'd be doing is taking this vector and stretching it out twice as long. Scaling the vector does not change its direction, it changes its length. And so, for example, 2 times vector v in component form would be 6, 8. So I'd have to go to the right 6 and up 8, and again the vector would be twice as long. Its magnitude would be twice as long as well. In terms of I and j, of course, this would be 6i, and that's the wrong I, sorry. Not imaginary number I, that's the italics one, plus, 8j. Okay. You can change the direction of a vector by scaling it with a negative number. So if we had negative v, then that would be -3, -4, and -3i plus -4j. Or, of course, you can just put -4 there. But in that case, you'd be going left 3 and down 4, and this vector would be going the opposite direction, 180 degrees in the opposite direction. Okay? And so if you did -4 divided by -3, you'd get the same angle that you would up here. So that's why you have to really pay attention if you're going in the opposite direction to change and make a 180 degree addition to your angle. All right, so that's what we mean by multiplying by a scalar. This number right here or this number right here is called a scalar. A scalar is not a vector. It's a single real number that does nothing more than scaling the length of a vector. And if it's positive, it stays the same direction. If you scale with a negative number, then you're changing the direction 180 degrees. So that's what that means. Vector addition is very simple. You just add components, one component plus another, component-wise. And we've already talked about finding the magnitude and direction. This is going to be using the Pythagorean theorem. This is going to be using a tangent function, or possibly sine and cosine if you want to work with the hypotenuse. And so that direction can be described by using what's called the direction angle if you do the inverse tangent. And then there's something called the dot product. So I'll end this short video by talking about the dot product, and the dot product is used to find the angle between two vectors. So if we had two vectors that shared the same initial point and they were going different directions, how would we find the angle between them? Okay, so for our last little bit here, let's say that I have vector v here, okay, and vector w here. Okay, so if vector v has components a, b, and vector w has components c, d, you know, possibly different from these two. If they're the same, then it's the same vector, right? But then the dot product is where instead of adding the components like you would do when you do v plus w, you multiply the components. So you do ac and then you do b times d, right? Now you don't make this a vector. This is not going to be a vector. This is going to be a number, and what you do is you take these products, AC and BD, and you add them. Okay, so this is called the dot product. There is another way to multiply vectors that's called the cross product, and you don't learn that in this class. You'll do that in linear algebra or calculus 3. Okay, but why do we need the dot product? Well, the dot product helps us find the angle between the two vectors. Okay, so there's a formula for that, and the formula uses cosine. So we'll write that here. The angle between vector v and vector w, we're going to say that that's theta, right? So the cosine of theta is equal to the dot product divided by the product of their magnitudes. Okay, so by dot here, we mean the operation where we multiply components and add. By dot here, we mean multiply the length of vector w by the length of vector v and the length of vector w multiplied together. Okay. All right. So let me give you an example, and there are rules about this. So, like for example, if the dot product between two vectors is 0, then that means the angle between them is pi over 2 or 90 degrees. So it means that the vectors are perpendicular when their dot product is 0. If the dot product is 1, it means the vectors are going in the same direction, same exact direction. If the dot product is -1, or sorry, if the cosine turns out to be -1, then what happens is, not the dot product, but if the cosine turns out to be 1, then it's 0 degrees. If the cosine turns out to be -1, it's 180 degrees, so that means that the vectors would be going in opposite directions. So let's go through an example of this before we go. Let's say that vector v is 2i plus 3j, and vector w is -2i plus 5j. Okay, so let's do a couple of things. Let's find the magnitude of vector v. Let's find the magnitude of vector w. Let's find the dot product. I always get those words backwards. The dot product of vectors v and w, and then we'll find the angle between the vectors. Okay, so the first thing we'll do is the Pythagorean theorem with the components. So vector v, we're going to do 2 squared plus 3 squared and do the square root. A squared plus b squared equals c squared. C is the square root of that, right? So this is going to turn out to be 4 plus 9, which is 13. Okay, same deal here. -2 squared plus 5 squared. So that's the square root of 29. Don't forget, a negative number squared is positive, right? So this is 4 plus 25. All right, for the dot product, we'll take the components and multiply. So we do 2 times -2 plus the product of the next pair of components, which is 3 and 5. So that's -4 plus 15, which is 11. So that's the dot product. And then for the angle, we just remember that formula that I put earlier in the video. So that is the dot product over the product of the magnitudes. So that's the square root of 13 times the square root of 29. And I can put both numbers under a single square root, right? The square root of 13 times the square root of 29 is the same thing as the square root of 13 times 29. All right, so how do I find this angle? I do the inverse cosine of this crazy fraction here. And I can do 13 times 29 real quick, so let's do that. That's 377. Okay, so in my calculator, what I have to do is I have to figure out the inverse cosine. Whoops. Okay, so make sure your calculator's in degree mode so that the answer makes sense. If you got 0.9 something radians, it is correct in radian mode, but more than often than not, they want the degrees. So it's 55.491 degrees. Okay, and again, type that in your calculator. Make sure that you're in degree mode. All right, so that's all for this week. If you have questions when you're going through ALEKS, and I realize this is a ton of information, you know, take this video and start checking off things that you know. The things that you don't know, go to Blackboard and view the video on that particular topic. And as always, if you have any questions, you can go to the discussion board and ask Mr. Molikash, or work with your classmates in the collaboration discussion board, but you can always send me an email. Thanks so much. Have a great week.